I'm going to start with the determining the truth of a conditional statement. This is on our page 14, Unit C summary notes. All right, and determining the truth of a conditional statement. A statement is false. There's only one way a statement is false, and we can see this a few different ways. We see it in this box right here. It's false if P is true and Q could be false. Okay, so if our hypothesis could ever be true and our conclusion could ever be false. In other words, if I could have a counter example. Counter examples make conditional statements false. So whenever we're finding a counter example, that's making our statement false. I think it was this class that came up with the table format where we were like, oh, X check mark true, check mark true, and so forth. So this would be this very last, I'm going to do this in red actually, this very last line of this table here where my hypothesis P is true, but my conclusion is false because I have a counterexample. This is the only way that my conditional statement ever ends up false. All right, so a little bit of explanation behind that. Then if either my hypothesis is false or if my conclusion is true, okay, so either if my hypothesis is always false or if my conclusion is always true, then my statement is true. So this was, I cannot prove it false because my hypothesis is so crazy. If you sprout a third arm. So I can't disprove that. Okay. And this one I can't disprove. This one I can't disprove because there's no counterexample. Like it is literally true. Everything about it's true, therefore it is true. So that is determining the truth of a conditional statement. And again, if you don't have everything written down right now, I'll put it back up. You'll have a chance to write some more down later. Conditional and converse statements, you can pull all that from your notes. I'm going to go down to, and then you also see the inverse and contrapositive. I'm going to go down to biconditional statements real quick with you. Our biconditional statement was where we take a conditional and its converse, and both of those are true. That makes a biconditional statement. Okay, so both have to be true for the biconditional to be true. If they ask, is this biconditional statement true? Well, is the conditional true? Is the converse true? And they're going to be in the form if A, then B, and then its converse, if B, then A. So we may need to find two statements that match so that the first part matches the second part of another statement, and the first part of this other statement matches the second part of the first statement. We have this crisscross matching effect. Okay. And we write these A, I, F, or if and only if B. And for this to form a good definition, I should be able to read it in my mind. A is always B, and B is always A. So if I tested a triangle is a shape with three sides. Does a triangle always have three sides? Yes or no? Yeah, you can't think of a triangle that doesn't have three sides. Does any three-sided shape, are all three-sided shapes triangles? Or let's say three-sided polygons triangles. Could you make a three-sided polygon that's not a triangle? All three-sided shapes are triangles. You can't really make one that isn't a triangle. So that would be a good definition. What if I said a polygon that has 4 sides is a square? Is that true, that all that all squares have 4 sides? Yes. Are all polygons with 4 sides a square? No. What would be a counterexample? A rectangle. A rhombus. There's a lot of things that could have 4 sides and not be a square. So that would be a bad definition. Okay? Because what we want, what a biconditional is 2 things that are perfectly and completely equivalent. The 2 sides are perfectly equivalent. Okay? Not just a description, but equivalent. This is my problem with a dog is a mammal with 4 legs. Are dogs mammals that have 4 legs? Does that define a dog? There's more to being a dog than just being a mammal with 4 legs, because there are other things that are mammals with 4 legs that aren't dogs. They're counterexamples. So that's not enough to be considered a dog, right? And then when they ask, is this biconditional true, and it's an equation with variables? Again, a biconditional is equivalent. So just solve for the variable and see if they have equal values. If they do, the biconditional is true. I'm going to ask again. We're just going to not communicate for a few minutes while we get through this, okay? All right. And I will bring this back up if you need to write some more down. We're going to go ahead and flip to the next page for now, though. Okay. Then for the number patterns, I want to point out these are some of the most common strategies we found. They don't necessarily represent all possible strategies. This isn't a list of everything that could possibly be ever, but they help build out the flexibility of our mind in considering what kind of strategies there could be. And these strategies could combine in different ways as well. So our first set was cubes and squares. So our squares, for instance, are 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so forth. Our cubes, 1 squared cubed, is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64, and so forth. I'm going to come back to this one in a moment, all right, because we're going to combine some of these together in ways. We could also have common differences. So maybe I start with 2, and I add 3 to get 5, and I add 3 again to get 8, and add 3 again to get 11. So I'm adding 3. These are my cubes, or squares. These are cubes. Okay. I could have a common factor. So maybe I start with 2, and then 6, 18, 24. What am I doing to each number in this case? Multiplying by 3. Okay. So multiplying by 3 in this case.
How would you get 54?
Sorry, not 54. 54. All right. These don't have to be increasing. They could also decrease. So I could have 17, 13, 9, 5. Subtracting 4. right? Or 24, 12, 6. Oops. Switch this over. 3. I don't know why, but my pen doesn't. Oh, just a second. There we go. 3, 1.5. What's happening in this case? Dividing by 1/2, or dividing, multiplying times 1/2, or dividing by 2. All right. Now, I could combine cubes and a common difference. So I could take these, for instance, take these squares, and I could subtract 1. So 1 squared minus 1 is 0. 2 squared minus 1, oops, use a different color. 2 squared minus 1 is 3. 9 squared minus 1 is 8. 16 squared minus 1 is 15. Okay, so this is x squared minus 1. These are my squareds minus 1. Or I could take my cubes, and I could, what did I do with this? Add 2. So 1 cubed plus 2 would be 3. 8 cubed plus 2 would be 10. 27 cubed plus 2 would be 29. 64 cubed plus 2 would be 66, and so forth. Okay. I could take my squares and double them. So I can combine these patterns together. All right, then we have the strategy of unsimplifying fractions. So I gave an example. What if we started with 1/24? They give us 1/24, 1/12, 1/6, 1/3, 2/3, and we're trying to find the next number. Okay, especially when there's not a clear pattern. Like I have 1, 1, 1, 1, 2. 24, 12, 6, like it starts to look like a pattern. 24, 12, 6, 3, 3. What's happening there? Okay, so unsimplifying my fractions can often help. Instead of 1/24, 1/12, I could rewrite these. 1/24, all over 24. 1/12 is 2/24. 1/6 is 4/24. 1/3 is 8/24. 2/3 is 16/24. Now what is my pattern? What's happening to my numerator? What's happening to it? No. I'm doubling it. 1 doubled is 2, 2 doubled is 4, 4 doubled is 8, 8 doubled is 16. What is 16 doubled? 32. So 32/24, and then I would simplify that to find a final answer. Of 4/3, which I might not otherwise get from the simplified fractions. Okay. In other cases, I might look at a set of fractions and see a pattern separately in the numerator and denominator. So we saw this in the example 3/19, 5/13, 6/10, 7/7. For this particular example, I left these unsimplified. 8/4, and so forth. In some cases, we can see a pattern separately in the numerator and in the denominator. What is happening in the pattern of my numerator? Increasing by 1, so my next numerator will be 9. There we go. What's happening in the pattern of my denominator?
You're subtracting 3.
There we go. So I'd subtract 3 and get
1.
Okay, and my next number would be 9. Okay, so sometimes our strategy is look at the numerator and denominator separately. Another pattern they like to throw in is the Fibonacci. That's where we take the first two numbers and add them together to get the next. So the beginning of a standard Fibonacci starts 1, 1, and then 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so forth. But then we can get variations on this. We could have Fibonacci minus 1. So 1 minus 1 is 0, 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 1 is 2, 5 minus 1 is 4, 8 minus 1 is 7, and so forth. So that's Fibonacci minus 1. An example that I've seen that is likely something like this might show up on the test would be where we double or triple the Fibonacci sequence, or maybe multiply it times 5. So the example I gave you guys was tripling. 1 times 3 is 3, 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9, 5 times 3 is 15, 8 times 3 is 24. The neat thing about the Fibonacci, so this is 3 times Fib. Oops. Okay. The neat thing about Fibonacci is it still fits even when it's been changed. So 0 plus 0, except for in this case, the beginning doesn't, because 0 plus 0 doesn't equal 1. So what it does in this case, when you're adding and subtracting, is this would be still Fibonacci minus 1. We'd have to add 1. 0 plus 0 equals 0 plus 1. 0 plus 1 is 1, plus 1 is 2. 1 plus 2 is 3, plus 1 is 4. So in that case, you could look at it that way, more than one way. In this case, when you multiply, the Fibonacci still works exactly. 3 plus 3 is 6. 3 plus 6 is 9. 6 plus 9 is 15. So the Fibonacci pattern, when multiplying, dividing still works exactly. Okay, here we go. And then the last one that can be maybe the trickiest to catch is increasing difference. So I've seen one like this, 5, 6, 8, 11, 15, 20. So typically a way to notice this is you're tracking those differences. So this was 5 to 6 was plus 1, 6 to 8 was plus 2, 8 to 11 was plus 3, and you start to notice the pattern. Okay, and so then you're seeing that this would probably be plus 6 to get 26. The trickiest one that I've seen was when we started with a duplicating number like this. Because we were like, oh, what's going on here? But this is literally plus 0. Oops, not 10. Plus 0, then plus 1, plus 2, plus 3, and so forth. And then we could see that this would end up being plus 4 for 19. You can go. Okay, so on and so forth. So just note that sometimes the first difference, you could also have a decreasing difference, but that's less common. So those are our number patterns. Our dots are going to go a bit faster. There's fewer things to write. Okay, our shape dot strategies and shortcuts. One was very simple. When we have some number of dots more than our steps, so for instance here I have step 1 and then have 2 extra dots for 3. Here in step 2 I still have 2 extra dots for 4. Here in step 3 I still have 2 extra dots. So I'm noticing this pattern. I call this step plus or minus k. In this case, my pattern, my number of dots, equals my step number plus my 2 extra dots in each case. That's my k. So that's one pattern that we might see. If I said find the number of dots in step 23, Well, that's going to be step 23 plus 2 extra dots would be 25 dots. I don't have to draw it all out. I can recognize the pattern and reason according to the pattern. All right, I call this next pattern my A plus B plus C plus D pattern. This is where we're seeing at each step we're adding an additional set of dots. So notice every step has this first single dot, and then starting in step 2, I'm adding this set of 3 dots, and then starting in step 3, I'm adding the step of 5 dots, and so forth. So instead of adding the dots up, don't look at the total number of dots, look at the pattern in the steps. Here, I have 1. Here, I have 1 plus 3. Here, I have 1 plus 3 plus 5. So if it were step 4, I would have 1 plus 3 plus 5 plus 7 in step 4. In step 5, I might have 1 plus 3 plus 5 plus 7 plus 9 in step 5. In step 6, I might have 1, 3, 5, 7, 9, 11. I don't have to draw a zillion dots. I don't need to try to find a pattern in the total number of dots. I can see the pattern in the pieces. Okay, and then when I find that, I can add some of them up to get the total. So that's my A plus B plus C plus D. And I will only give you, for dots, I'll only give you one of these kinds of patterns. I'm not going to throw something at you from left field. Okay. All right, 2 left. A times B pattern. This is when we're getting some multiplication array. It's a rectangle. In this case, I start with 1 tall times 2 across. Then I have 2 tall times 3 across. Then 3 tall times 4 across. What will my 4th step be? 4 by 5. My 5th step would be 5 times 6. What would be my 10th step? Yeah, 10 and 11. So notice in each of these, my first number matched my step number. If I can find a pattern, a connection, relationship between my step number and one of the numbers in the array, then I can find it for any step number. I don't have to do every single one in between. So I noticed that step 3 was 3 by 4, so step 10 will be 10 by 11. That's my pattern reasoning, my inductive reasoning. It saves me time. It's a good shortcut. And then finally, we have something very similar, but based off of squares. So in this case, step 1 is 2 by 2 or 2 squared. Step 2 is 3 by 3 or 3 squared. Step 3 is 4 by 4 or 4 squared. What would step 4 be? 5 squared. What would step 10 be? What's that?
No, sorry, 11.
11 squared, because I notice that in this case, my square is always 1 greater than my step number. Having 1 greater than my step number. All right, so that's the pattern. It could be 2 greater than my step number, but I had really large dots and I could only fit so much in the space. It could be if I can't really go smaller than my step number because then I have zeros. So it's going to be some number greater than my step number. Okay, so that's our inductive reasoning, our main strategies and patterns. Any dot questions are going to be one of these 4 strategies. Number patterns could be any combination of these strategies. I'm not going to throw something at you completely out of left field. And then you are responsible. You can use any of your notes. Inductive versus deductive hypothesis and conclusion comes from your 2.1 and 2.3 notes. as does counterexample and negating a statement. And then pull this out and all of this other stuff. Oops, deleting too much there. Where is what I was looking for? Give me just a moment. I understand. I said give me just a moment.
Caesar. Don't do that.
There we go. And then conditional, converse, contrapositive, inverse all comes from your 2.2 notes. So you can fill those in from there. All right.